Hello?
Hello. Hey.
I can see you. Can you hear me?
Yes, we can. Can you hear us?
Yes, absolutely. How are you?
Brilliant. Yeah, great. And great to see you as well. Okay, I'm just going to make full
Great
screen.
to see you too.
Let's go with you. Full screen. Okay. And then speaker. Yes. No. View. Just do view and more options. Hide me. There we go. Yeah. Okay. If you do want to share your screen or share anything, that should come through fine on our end. So brilliant.
Okay, let me try that.
Cool. So for anyone who hasn't, do you have an intro, or do you want me to do an intro?
Oh, you can do an intro, but am I sharing my screen? Can you see this?
Yes, we can see it. Yeah. So
Awesome.
Brilliant.
And sorry if I didn't have time to change any of this. There was a disaster with some friends at the weekend. I was going to change the slides. You're just getting the old dates, but it's fine.
No worries. Okay, cool. So this is, for everyone who hasn't met Heloise before, this is Dr. Heloise Stevance. She used to work here in Auckland, so working at the University of Auckland. Her specialty, I believe, is supernovae, yes?
Yep, that's right.
One of them, and she has come to speak to us before, but now she's working over in the UK, doing research over there. So yeah, thanks so much for joining us tonight / this morning, Heloise. It's great to see you, and I'm looking forward to hearing what you have for us.
Thank you. So sorry for the little delay this morning. It is 7 a.m. in the UK, and as I was walking into the office, I realized that the park that I usually walk through is closed before 7 a.m., so I had to take a long detour. So the talk I'm going to give you today is the talk I gave for my Caroline Herschel talk, which is a prize that is given once a year in the UK. I received it in 2024. And it's a talk about the stuff that I do in my current work, which is studying exploding stars, yes, but specifically I create automated systems, I create machine learning systems to help us find these explosions. So the story I want to tell you is not the details of the maths of how I do stuff, but really explore that relationship that astronomers have with new technologies and how that can bring new progress. So let's take a look at how new techs have given us new knowledge. So it starts with the first telescopes, which some of you in the room will know more about than me. You'll be better at the history. But obviously the moons of Jupiter can't be seen by eye. You need telescopes to be able to observe them, and Galileo was the first one to do that. He was the first at pointing telescopes at the sky, originally that were used to find ships, enemy ships at sea. Photography in the 19th century brought astronomy into the Industrial Revolution. For the first time in history, astronomers were able to take pictures on the large scale, not just do drawings by hand, and that's what gave us the very first catalog. So if you've ever seen stars, for example, with the HG and then a big number afterwards, that's the Henry Draper catalog. It's one of the first large-scale catalogs there is out there. And then in the mid to late 20th century, we got the technological revolution with semiconductors that gave us the chip, the computer chip, that made computers go from something that fits in a big room to something that fits on your lap. And obviously, the digital camera. So that's semiconductor technology. That's what allows us to go from photographic plates to large arrays of pixels. This is a slightly old example. Maybe I should have showed you a picture of the Vera Rubin observatory camera. That's the biggest camera ever made. That camera is so big that there is no screen in the world that can display with full resolution the images that it takes every night. And finally, rocketry. Rockets were a big deal for astronomers because the atmosphere, as you probably all know, is a pesky little thing that makes our images blurry and wobbly. And it also stops us from seeing things like ultraviolet and X-rays, which are very, very interesting arrays of the light spectrum. So if you send your telescopes out into space, like the Hubble Space Telescope or the JWST, you can get beautiful pictures like this. So this is the ultra deep field, which most people will be familiar with. Here, I've cropped a small part of it that is maybe only 100 times smaller than the moon, and you can see hundreds, if not thousands, of galaxies. I've not counted them all. And these ultra deep fields are things that we do now with every new commissioning. JWST has a beautiful ultra deep field image. Again, this is only a small part of it. And the Rubin Observatory is currently observing really deep fields. We call them deep drilling fields. And I hope that in the next few months or in the next year, I'll be able to put these in my talks because they're going to be absolutely fantastic. Now, the reason for this introduction is obviously to give some context, also so that I can show you some of the most beautiful pictures that we have. But the point I'm trying to make is that really progress in modern astronomy is a partnership between people and new technologies. These two things come hand in hand. And so when new technologies arrive on the scene, then scientists get excited. New technologies, maybe new science, maybe new knowledge. And that's something that's happened with the wave of machine learning and AI over the last few years. So now, before I go deeper into the ML stuff, let's talk about what I actually do, what people like me do, people that look at the transient sky or the sky that changes. So here's a picture of me at a telescope a couple of years ago. I'm very lucky that I get to go to places like Chile to observe with things like the New Technology Telescope. Now, as you may notice, a lot of clouds in the sky. Not ideal if you're an optical astronomer because you can't really see anything through clouds. Now, fortunately, the clouds were very quickly blown away by extremely strong winds. Winds so powerful that we could not open the dome of that telescope because if the winds are too strong, then things can fall off the dome onto the mirror, which is bad, very, very bad. So I had a lot of time during the night to take pictures with my phone, take pictures of the night sky. So that's a 5-minute exposure taken with the very phone that is counting down the time right now. And you can see the center of the galaxy and details of the interstellar clouds, pictures that you must have even much better versions of with your own cameras and your own telescopes. But I was very impressed with what a phone can do. Here is a much better one that someone took with a proper camera at ESO. You can see some beautiful colors in there. Now, when you look at the night sky, it doesn't look like this because our eyes are not cameras and we can't take 5-minute exposures. We can't do that. At best, in the darkest of skies, our eyes can see a few thousand stars. But a telescope like the Sky Survey that I've been working with over the past few years, the Sky Survey Atlas, can see 1 billion sources in the night sky. Now, to give you an idea of scale, a few thousand seconds is how long this talk will take. 1 billion seconds is over 31 years. So completely mind-boggling orders of magnitude. And these stars or these sources can change. So obviously, so the sky is very big and it changes. We've got, here's an example of Orion. By the way, you can see Orion is the right way around for New Zealand. I made an effort. I make an effort in my talks, even in Northern Hemisphere, to put Orion on its head so that people in the Northern Hemisphere don't think that their way around is the right way around. And so Betelgeuse in the shoulder of Orion is very variable as a star, which is cool, but it's not the kind of stuff that I want to study. Other things that change are comets and asteroids. Here you've got an example of an asteroid kind of exploding because people shot many satellites at its moon, Dimorphos, and Atlas captured the cloud of dust that was ejected by that. So these are cool, but not what I study. And the kinds of stuff that happen in very distant galaxies are also very interesting, but very diverse. You've got supernovae. Mitchell mentioned that that's the kind of stuff I do. So stars that explode at the end of their lives, and they make the stuff that we're made of, the oxygen we breathe. Sorry, I can't really hear what you're saying. So if you're participating,
Then our sun.
Yes, Yeah, so supernovae, okay, so there's two kinds of supernovae. Supernovae from massive stars, so massive stars are born with more than 8 times the mass of the sun roughly. And there's another kind of supernova, type 1A supernovae, that come from lower mass stars that have turned into white dwarfs. So our sun will turn into a white dwarf. And when these white dwarfs gain too much mass, so become more massive than roughly 1.4 times the mass of the sun, they undergo a thermonuclear runaway that makes them explode. And these are also really interesting because they make most of the iron in the universe. And because they are standardizable candles that allow us to measure how far things are in the universe, and that's what's given us the best evidence for a universe that not only expands, but expands at an accelerating rate. So supernovae of all kinds are fantastic probes of where we come from as people, but also where we're going as part of the cosmos. So thank you very much. Very good point. Other things that go bang, tidal disruption events, that's the hungry black holes. So stars that come too close to a black hole and then get disrupted. It creates a flash. And then loads of other things. The point I'm making here, because I'm not going to be able to tell you about all of these different astrophysical events, the point I'm making is these things change on very fast time scales. So their light goes up and down on the scales of days, weeks, or hours, or days, which is very, very fast on the scale of the universe, especially if there's a billion sources in your night sky. So the point is, in this day and age, we need to not only map the sky across its vast expanse, but also we have to do it over and over and over again if we want to study these really cool events. And that's very difficult. So to do this, we have astrophysical surveys that have really big cameras. Now, here I'm showing the field of view of some of these surveys, not to scale on the whole sky, but to scale with respect to M31 or Andromeda and with respect to the moon. So you can see one of the Atlas field of views. Here it says ×4 because it's out of date. We now have 5 telescopes across the world, not 4. Here is the Vera Rubin Observatory, so slightly smaller field of view than things like Atlas or the Zwicky Transient Factory or GOTO, but it much more detailed, much better plate scale. And so with these kinds of surveys, we can take this sort of movie of the sky. Now, the survey I'm going to focus on a little bit is Atlas, although I've mentioned Rubin because that's what I work with these days. And Atlas is the Asteroid Terrestrial Impact Last Alert System. It was initially designed to find and track near-Earth asteroids that could potentially be dangerous for life as we know it. And so there's, like I said, the slide's out of date. We've got here 4 units, 2 in Hawaii, 1 in Chile, 1 in South Africa. There's also 1 in La Palma. You can see just the faint outline of that red dot there, which I had hidden at the time because the telescope was not quite commissioned. So it was sort of an Easter egg, but now the telescope is working and we are taking data. So we've got 5 units, both in the north and the southern hemisphere. So we've got this sort of 360 view of the world, of the sky, I should say. Now, in addition, Atlas can go back to the same patch of sky really, really quickly. Oh, interesting. I can't remember. Hang on, let me just check. When did I change this? Now, this is cool because you guys are nerds in the best way possible. So actually, you'll probably be interested in this. But I just want to make sure I don't take you down a talk that's too long. I don't remember putting all that in. I might cut some of it in, but the specs, you'll probably be interested in it. Because Atlas is surprisingly small. It's a Schmidt telescope on a German mount. You can see the counterweight over here. It's got an aperture of only half a meter. I can't remember what it is in inches. Sorry, I can't really help you with that. And it's got a really fast focal ratio. And that's why we've got such a large field of view. And that's why we can go back to the same patch of sky so quickly. So Atlas roughly has a cadence of 24 to 48 hours. And what it does is it goes... on one night, it observes the same patch of sky 4 times. So you go once, then you do a bunch of other pictures, and then 15 minutes later, you go another time, and then you repeat that. And this is good for the people looking for asteroids, because over the course of an hour, if you've got 4 pictures, you'll see the asteroid go bam, 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 bam. So that's what I said here. We've got that kind of cadence, 4 times 30 seconds. Yeah, 30 seconds is the exposure time, and that gives us a depth of nearly 20th mag in a single image. If we stack the shots, we can go beyond 20th mag, but it's usually a little bit hazy down there. And we do saturate at 12.5 mag, which means that when there's a very bright star nearby, sometimes we get flares that we have to, and scattered light that we have to deal with. We are using only 2 filters, orange and cyan. Mostly the orange, to be fair, and we don't change the filters during the night because the telescopes are kind of independent. We don't have someone that's observing there. They're remotely controlled. In fact, there's one in Hawaii that is cut off from the world because of one of the Hawaiian volcanic eruptions. Like, we're using solar power because there's no power lines anymore, and we are using internet via satellite because there is no internet connection via cable. So because we can't change the filters easily, we've only got 2 filters that are really broadband. The sun goes in when the moon is new or when it's close to new, because otherwise the sky is way too blue and it ruins our limiting magnitude. But a lot of the time we are using the orange filter. And here you can see the sort of background that we're dealing with. All of these down pointing arrows are the limiting magnitudes at a given time, and you can see that it goes up and down over the course of a month because of the moon, because when the moon is bright, the sky is bright and it affects our limiting magnitude. So that large field of view allows us to go back to the same patch of sky. Oh, there's a mistake there. Every 24 to 48 hours, depending on exactly the observation strategy of that telescope. Okay, so that allows us to study things that it was designed to study, like the near-Earth asteroids, but I personally don't care about them. I care about supernovae. I care about things that go bang in very distant galaxies. So there was a little bit more of detail about the low mass stars and the high mass stars, but we've already covered it, so I think we're going to be able to skip that bit. I can show you, that's called the black hole, the tidal disruption events. That might be something you don't see or hear very often, so I'll show you this cool video. So that's an explosion that happens because a star gets a little too close to a black hole. Not too close. So we've got an artist impression of a black hole here, and we've got a star coming in hot, coming in fast. And as you'll see, as it gets closer, it gets distorted by the gravity of the black hole. It becomes like oblong. And when it gets very, very close, it gets fully disrupted, and half of the star is ejected out into space. And the other half like falls back onto the black hole, and you can see it starts shining. And that's not the black hole itself, because the black hole is black. It's the matter around the black hole that it can't enter the black hole at an infinite rate. It doesn't do it instantly. So there's a traffic jam, essentially. There's a traffic jam of matter. It causes a disk to form around the black hole. And just like real life traffic jams, things get heated. And because the material gets really hot, because the material gets really hot, it gets really bright. And so you get this flash of optical light, but you also get flashes of X-rays, and you get some really interesting stuff that allows people to study black holes that would otherwise be invisible. It allows you to figure out their mass and their spin, and it allows you to understand the black hole population that is way too far in the universe for us to understand. So black hole physics. Now, the problem with these different kinds of explosions, why is it only partially full screen? This is super weird. Sorry, I've got a, yes. Ooh, it didn't like that. Things are loading. Can you see this? We good? Cool. So we've got these different kinds of explosions. We've got the different kinds of supernovae. We've got the tidal disruption events. We've got the kilonovae, which I skipped a little bit. There's not very many of them. But the point is, there's not very many of these objects. Thousands of supernovae sounds like a lot, but it's not like the billions of stars we have in the Milky Way. In the Milky Way, we've got between 200 and 4 billion stars. So they're pretty rare events. And in order to study what we want to study, which is the origin of the elements, the expansion of the universe, probing black hole physics, we need to find these. We need to find these objects that are really hard to spot. And so we need to play a game of spot the difference with the universe. So let's play a little game. Now we're going to go back towards the machine learning side of things now. And we're going to play spot the difference with these two pictures. These are like cropped bits of that picture of the Milky Way I took with my phone a couple years ago. I showed it to you at the start of the talk. Can you tell the difference between this picture and this picture? Can you see that this one looks blurrier? It looks like there's more pixels. And this one looks much smoother and like it's higher resolution. Now, these are the exact same pictures, the exact same exposure, but I made my phone save two files, one a JPEG and the other one the RAW. But what I found very surprising is that the RAW image, which normally is the one with the highest resolution, because JPEG is a lossy type of compression, the RAW image was blurrier than the JPEG. And the reason that is because my phone is not just a normal camera that just takes pictures. It is a smartphone that tries to do magic maths to make my pictures better, because that's how they market these phones. And so the extra resolution we've got here is artificial. It's done with generative AI. At least that's my best guess. It's a Google phone. Google is not exactly open source. But I know that there's some form of generative AI going on there. By generative AI, we mean it generates extra stuff. So in this case, it generated extra pixels, extra resolution. And in this case, it did a pretty decent job. It's pretty good. And so that kind of brings us to the question of what is AI? Everyone throws that word around. It's been going on for a few years, that train of hype. And if there's one takeaway you take from this talk, I usually do this as a sort of audience interaction, but I'm going to be honest, I can't really hear what's going on, so this is probably going to be a little too tricky. But the point is, AI is just a marketing term. I really want you to come out of this talk remembering this. Artificial intelligence is a marketing term. It's something that is not new. It's been used as a sort of like branding or marketing term since the 60s. It's come in and out of fashion at different points in history. It meant different things to different people. So AI itself doesn't mean much. So the word that maybe means a little bit more is machine learning, but even that has its own branding issues. At the end of the day, a lot of the AI that you see around your everyday life is just statistics. Obviously, that's a lot less sexy, right? The marketing department doesn't like the word statistics because everyone falls asleep when you mention it, but it is just statistics. But you know, statistics are cool, and we're nerds here, so let me tell you a little bit about stats. I'm not going to show you any maths because it's late for you and it's early for me, but I'm going to try and teach you a little bit of intuition on what machine learning is. And all that machine learning is teaching your computer a function. A function mathematically is just a box that takes an input and creates an output, creates an answer. Now, in this analogy, we're going to use the analogy of a DJ deck. So you put some sounds in, you turn some knobs, and slightly different sounds come out. Now, I've never used a DJ deck. I've seen people use them. I don't know how to use them, and you don't need to know how to use them either. But you just need to understand the concept that you put some sounds in, and then you turn a few knobs and dials, and then you get a different sound out of it. Now, the problem we've got in this analogy is that we have some sounds that can come in. We know what sounds we want to come out, but we do not know what the knobs and dials do, and we've lost the manual. We've lost the manual completely, and all of the numbers have rubbed off. So what we're going to do is we're going to just start turning random stuff and see what comes out. Right? And we're going to learn how to use our DJ deck by just trial and error. And when things start to look or sound slightly better, then we get positive reinforcement because we're happy that the crowd's dancing. And when things go badly, we're like, oh no, let's not do this again. And that's what we're doing with machine learning. We're learning a very complicated function. You may have seen this HKCD. It's from nearly 10 years ago now. It was before the craze of AI, but when machine learning was the word that everyone was using. And the concept that it's just a big pile of linear algebra that you keep on turning until you get the results that you want is remarkably accurate. Maybe worrying, but it's good to be aware that this is exactly what's going on. It's a linear algebra that is too complicated to understand on its own, but you can understand the inputs and the outputs. Now, I would argue that the reason people are happy to use the word AI sometimes, artificial intelligence, is when a machine does something that you didn't expect a machine to be able to do. So when you're surprised that a computer is able to perform a task, then you think, oh my God, is it becoming sentient? Is it closer to humans? But that changes culturally over time. There are things that would have been called AI or would have been of the realm of science fiction in the past that we take for granted today. One of these examples is computer vision. So you take for granted the fact that you can unlock your phone with your face, or that Facebook recognizes your grandma in the pictures that you post, or that a speed camera can take a picture of your car, automatically read your number plate and send you a fine. That's not considered AI anymore because we are living with it. But for a long time, computer vision was the realm of science fiction. It only started getting better in the 90s with something called the convolutional neural network. This GIF, by the way, is an original GIF explaining these from the late 1990s. It's from 1998, and this guy's the guy who came up with this. His website is still up and still looks like the original HTML. It's amazing. It's honestly a great time capsule. So what made computer vision good is a couple of things. So it started getting good in the 90s because of the method, but it kind of got stuck for a while. And the reason it got better is because a very large data set of labeled images was released in the 2010s. And competition arose that said, take this large data set, train your machines to do computer vision recognition. So tell me whether this is a cat or a dog or whatever. Let's see if you can make computers that are better than people. And very quickly, teams around the world managed to achieve superhuman performance. That was the start of what we call deep learning, because we had this kind of tool that now could recognize most things in images, not just numbers and digits, better than human in many benchmarks. But in order to do this, you needed very, very large functions, very, very large DJ decks. So this first one that I showed you here, the one that just recognizes handwritten digits, that requires 60,000 of these knobs and dials. The one that won the competition in 2012 and kind of propelled the deep learning revolution had 60 million of these knobs and dials. And people started realizing that bigger models give bigger results, at least for some of these tasks. And the reason I point this out, the start of the Facebook AI lab in 2013 as a result of this stuff, is because AI was not a term that was used at the time in the early 2010s, because you would have sounded like a crackhead, honestly, because AI had been so overused in the 20th century that people didn't see that word seriously. But Facebook sort of reclaimed it, and now here we are 13 years later, and we're using it everywhere. So just to point out the ebbs and flows of the hype. So what made this breakthrough come through? It's a mixture of it's a perfect storm. So it's a mixture of data and computational power. So in the mid to late 2000s, we had the acceleration of social media and digital cameras and smartphones being present everywhere. So everyone was taking pictures. So much easier availability of data. The other thing is much easier access to things that can do the linear algebra, the pile of stuff that guy was standing on in the meme earlier. So GPUs were becoming much more widely available because of video games and because of the CGI industry for movies. So that started in the late 90s, well, late 80s, early 90s. GPUs to do the graphics. They also need to do linear algebra really, really fast. And that's perfect for machine learning. So if you combine these two things, you get really good computer vision, which now you take for granted. We just know that it works and we use it in everything. And so for astronomers, what that means is you can take maths and data and you can teach your computers to classify images. And it is something that we do all of the time now. We have our machines spotting the difference for us. Here we've got an example of a before and an after. So this sort of egg-looking thing is a galaxy. And here you might see a faint little extra dot. And so if you subtract the after from the before, you can see this bright little thing left over. Everything else here is noise. We just have one bright dot, and that bright dot is a supernova. And this exercise of taking a before and an after and taking the difference, that's what we do constantly with a telescope like Atlas or with something like the Rubin Observatory. The problem is it goes wrong a lot of the time. Here you can see a lot of speckled dots. They are not real differences, but they can be mistaken for real differences if you just do a dumb algorithm that says, if bright, then difference. That doesn't work, because all of these are bogus, they're bad. And if you were to do this by hand, you would have a massive issue, because we get tens of millions of these differences every night, but only a handful of the really interesting things that we need. It would take me, it would take a single person an entire year to play that spot the difference game with one night of Atlas data or of Rubin data. If they didn't sleep, didn't eat, didn't do anything else, it would take someone an entire year. So obviously we need to automate. We need to automate on a really large scale. So how do we automate? Well, we've got a few things that we can do. We've got tens of millions of alerts of potential differences coming through. The first thing we do is we do basic cuts, like we have 4 images of the same patch of sky. If less than 3 of those show a difference, then it's probably an accident, it's probably a bogus, so you don't look at it. The other thing you do is you remove known variables. So if you're like me and you care about stuff that exploded in different galaxies, you don't want to find Betelgeuse every night. And so you know the position of Betelgeuse. If there is a difference at the location of Betelgeuse, you say, okay, it's probably Betelgeuse doing something. We're not going to look at it. But when you're done with this, you still have thousands or tens of thousands of differences to look at, and that's still not workable. So the first thing we do is a convolutional neural network, just like the handwritten digit or the ImageNet competition. Now, in our case, we just look at the center of the difference image, and we ask our CNN, does this look real? And it gives us a number between 0 and 1. And everything that's below a certain value, in this case 0.2, is labeled as garbage. And just this simple task removes 98.5% of the garbage. Now, the problem is there's a lot of garbage. It is very difficult to spot the difference with the universe. And even when you do this, you're still left with hundreds of things to eyeball every day. And that's before we added the new telescope, the 5th unit of Atlas. Eyeballing, by the way, is a technical term. That is a technical term we use with astronomers. That is the technical term we put in our papers. Eyeballing is just the act of looking at the data and deciding whether it's real and worth doing astronomy with. And so this is a breakdown of what's left for people to eyeball before I do my job. So 85% are still bad. And in the leftover stuff, you've got about half of it that's galactic explosions or outbursts. Interesting, but not what we want. And the rest is potential supernovae, tidal disruption events, and other extragalactic explosions. So it's time-consuming and it's not very satisfying because a lot of it is garbage. But the eyeballing task is not easy. So this is the kind of stuff that we look at and the kind of information that we've got going for us. So we've got the stamps, the before, the after, and the difference. We've got the location on the sky. We've got the location with respect to an underlying galaxy or host. Here you can see it's a quite interesting galaxy that's got some interaction going on. We've got some context that's given to us, like which galaxy is it related to, if any, how far is it from the center of the galaxy, how far is that galaxy compared to Earth? Is it like 100 million light years? Is it 200 million light years? And then we've got the light curve, which in this case is optimistic. It's a light point. We have one night of detection. Everything else is those narrow, those down pointing arrows I was showing you earlier that tell you the limiting magnitude of the sky. That's why it goes up and down. The moon becomes brighter and fainter. And here we've got, it's the first time we've observed this explosion. It's just happened, so we've got just one point. And that's when we have to decide whether this is real and interesting. But humans are really good at this. They're really good at figuring out with very little data whether this is real or interesting. And the computer needs to try and emulate this without making us lose opportunities. And that's what my virtual research assistant, which is the thing I've been building, does. Now, I'm very aware that is in this day and age, the word virtual and assistant make it sound like it's ChatGPT. It is not. I promise you, it is real solid statistics that I understand. But I picked that string of words many years ago when I was writing my funding application. And now I am forever having to explain to people I didn't just put astrophysical data into ChatGPT and hope for the best. So what my VRA does is it takes the data, those hundreds of alerts that we would usually eyeball, and it does some ranking before the eyeballers and only shows them the stuff that is the most likely to be interesting for them. And that reduces our eyeballing task by over 80%. Now, this is a very outdated plot. Here is, I'm just going to see if I can find Slack and show you the real actual, come on, Slack, don't be a dick. The real actual plot, oh, there we go, from last week. So here is a plot from the last few weeks. This is, the gray is how much the VRA has done. That is because we've had a slight issue with our telescope, you see. Usually we get a few thousand things after the CNN, we get a few thousand things the VRA has to look at and tell the eyeballers whether to actually look at them. Now we're looking at of order 30,000 things coming in every week. That's because there is a hardware issue with one of the telescopes. But the VRA is decent enough at its job that when there is that kind of dramatic issue, it can take on a lot of that work, and it means that we can stay in operation. If the VRA wasn't there, the CNN doesn't do a thorough enough job, and we would be bombarded with thousands and thousands and thousands of things. And it means that we would have to stop what we're doing and try and figure things out, whereas now we have a little bit more time and we can keep observing the sky, and that's really, really nice. How am I going to tell you the details of this? That's kind of boring. I mean, the point is it takes inputs and outputs, and the inputs that it looks at is exactly the kind of stuff I described here that the eyeballers are looking at. It's just I found a way to make it easy for the algorithm to take that data in, so it doesn't have to look at a web page. It can just look at the numbers, and then it asks itself the same questions that astronomers ask themselves when we look at a page like this. Is it real? That's question number one. And is it galactic? And then it just gives a score between 0 to 1, between 0 and 1 for both of these questions. Is it real? Is it galactic? And then we've got this space where real extragalactic things, the blue things I'm interested about, all of the supernovae, tidal disruption events, and superluminous supernovae in blue congregate in this corner of the plot. And then the very final step for ranking, because that's what we want to do, we want to see the good stuff, that stuff that is the best and the most interesting, we want to see it at the top of the list. So how do we rank this? Good old-fashioned Pythagoras. So it's 4,000 years old, but it still works, baby. If it still works, don't change it. For all of the people that say, why do I need to learn Pythagoras in school? Because sometimes you need it in real life, okay? Here is a real life example. Maybe not the most relatable, but a real life example that Pythagoras is useful. And by just literally doing that geometric distance, we get this. We get something that takes on over 80% of the workload off of the humans. And so I think to go back to this point I made earlier, that progress in modern astronomy is a partnership between people and new technologies. Really, progress in science is a partnership between people and the right technologies. And the technologies don't have to be new in order to be the right ones. Here we have a mixture of, and I think I've put the date here, LightGBM is the specific algorithm that I use to do that classification. Is it real? Is it galactic? That's from 2017. It's a really smart technique. But Pythagoras is 4,000 years old. And when you combine the two, you get the thing that works. And hang on, so I've been talking for about 40 minutes, and I think the rest of the talk is kind of more machine learning-y, and I don't think it's as interesting. So I'm going to leave it here, and if you want a more machine learning-y rant about ChatGPT and blah, 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 we can have that. But otherwise, I'm just going to leave you with a pretty picture, and you can ask me any questions.
You guys have questions?
Yeah, any questions?
Any questions? Questions? Yes, no. Yeah.
Oh, actually, why don't we turn the lights on? So.
Oh, yeah. Go back.
You're just turning the lights up.
Yeah.
All right.
Yeah, you can see us?
Hold on, I need to... Yes, I can see you, yes.
Cool.
Okay. Cool. All right. Just... Here we go. I'll just relay any questions if they're not there.
Because the variability of things changes, how many comparisons do you take of a particular event? Because you've got a time history. Do you take 1 or 10 or as many as you need?
Oh, that's a really good question. So, like, how will we build the reference image? That's a good point because, for example, when you have a new telescope, and we're going through that with Vera Rubin, and it takes images of the sky for the first time, there's supernovae in there, right? So there's things that are there now, but they're not going to be there in 2 months. And so actually you have to take a few images. So how many, it depends. So I'm not the one that builds the images, the reference images, but it doesn't have to be hundreds. It just has to be enough to be deep enough, right? So that you are noise limited in that, and not like, oh, the moon was bright, so the sky is bright. And you need to have a long enough baseline that you can average out things like supernovae or an asteroid coming through, that kind of stuff. So it takes a few months at least to build that for an individual patch of sky. But then you also have the problem that it takes 1 year for the Earth to rotate around the sun. And so to see your whole sky, it doesn't take 12 months, but it takes about 8 months or something like this, depending on exactly how high your horizon is and everything. So it takes several months to build the template in the first place, and then you need to rebuild them occasionally because nearby stars are close enough that they literally move because we're moving in the galaxy and they're moving too. And so we do have some of these differences in the galactic plane. There's a lot more garbage differences because stars have literally moved in our field compared to the template from like 4 years ago.
Cool.
Any other questions?
Question?
Oh, yes.
Go on, Andrew.
When you're trying to reduce that data down to get rid of the garbage, how much risk is there in your algorithms using to do that actually filtering out good stuff, or because some bias to there? Is there a bias? There could be some sort of bias in your learning model because that's all we know, and you're trying to discover things we don't know.
Yeah, that's a good point. So that's something that's always on our mind. It's always on my mind, especially for the VRA. So for the CNN, it's a bit easier because the question it's asking basically is it PSA-like? Like, is it a point source? And so sometimes, sometimes it does happen that you have something that is literally garbage because the PSF is garbage, but there happened to be a real supernovae in there. But then on the following night, where things are going well, you'll find it. But the CNN is not as bad because the PSF is a PSF. For the VRA, it's more of a concern for me, and it's something that I've obsessed about a lot. And so what I've done in the early days when I was validating the VRA is I have bots that look at what other telescopes have reported. So what other teams have reported to the rest of the community to see if there's anything that I have missed. And every week I have a little report that points out things that the VRA scored low, but other people found and therefore are real. And I have not found anything that the VRA has missed. There was one example that I found in the early days, and it was just bad luck. It was the moon was bright at one point, and so we had a few detections, but not enough. And then, so it was sort of a fluke. And so I've looked at it a lot, and it's not astrophysically biased. It's just bad luck of like, oh, so there was a stellar flare here, or like the moon was bright, and so you will get a few of these losses, but it's not looking at specific like astrophysical like light curve things for that specific reason. That I don't want to be finding only supernovae that I know about and then ignore everything else the universe is sending to me.
Any other questions?
No, I think we're good.
Okay, great. I'll just...
You know, with the virtual thing, is there, do you keep all that stuff on record? Like the virtual assistant stuff? All the pictures?
Sorry, I didn't catch that. Can someone repeat closer to the microphone?
So the question was, do you keep a record of all the pictures and all the data?
That's a good point. Yes, we have a record of all the pictures. We have all of the data, and I keep a record of all of the scores and the things that the VRA has done. There's a full history in case something goes wrong and we need to know why. So, and also the garbage thing, I should say, when the VRA says something is garbage, it labels it as garbage. So this data is literally still in the database. Occasionally, like once every couple of years, we will clean the garbage out, but by that point, if it was to be found, it would have been found by someone, by us, when it's bright enough or bright enough the telescope. But on a day-to-day basis, if the VRA says this is garbage, we are not deleting pictures. I'm not even deleting the alert information. It just gets labeled as garbage, and so that when a human goes goes to the website to look at candidates or things that are interested, it's just not the first thing that they see. But we do absolutely keep everything, especially in the first instance, because we're paranoid about things going wrong.
One more question. Can we have a look at those pictures, or only you? And your team?
Are they public?
Can we give a look? What? Sorry.
Pictures, are they publicly available, or are they just accessible to your team?
The pictures are you can't access the pictures, but you can get the line curves using the force photometry server. But maybe that's not as interesting because line curves are just points on the graph, whereas pictures you can do stuff with. Atlas doesn't have the best resolution, to be fair. So you know, it's 1.8 arc second per pixel. So I think some of you guys will have better resolution than that on your own telescopes.
Once you find a supernova, what do you do with it?
That's a good question. So once you find it, so every week we have what we call the data wrangling meeting, where we look at all of the things that we have found this week and whether we want to follow them up with other telescopes. So we've got telescopes that have spectrographs, and we can go and take spectra the supernovae, because that tells us about the composition, the velocity of the ejecta, and all of the other things. So really the finding thing is, it's not even it's step 0 of the science. It's not even step 1. Finding is not enough. But there's not very many spectrographs in the world, and so deciding what is important enough to dedicate telescope time is actually where we want to spend most of our time, because it is tricky, and that's where the science is coming from. So yeah, there's a lot of taking more data with other telescopes, whether it is better light curves with more filters or spectroscopy to get further information.
Interesting one that you've studied so far.
Oh, that's a very interesting point. Oh, there's a couple that come to mind. There's one that we still don't know what is going on with this one. There's one, it looked like it exploded twice. It makes no sense. Literally like 2 years apart. There's 2 supernova-like light curves. The second one looks like it was less stripped than the other one, so that doesn't make sense. So we don't understand one. There's the one that was the coolest for me to eyeball live was one in 2024, literally the 31st of December 2024. I was on eyeballing duty on New Year's Eve, and I spotted something that looked like a supernova, but it was already registered. Like in 2022, there was already a supernova in that spot. But I could tell by eyeballing the thing that it was definitely real. It wasn't a bogus that happened to be in that same location. It was just another explosion in that spot. And again, we still don't know what that is. We're still actively trying to study this. It could be that you have 2 stars, so binary stars, orbiting around each other, and one of them goes supernova and leaves behind a neutron star that then gets kind of slingshot into the other one. So that's a possibility. But it could be, we don't know. Honestly, we don't really know. But even that has loads of problems. There's loads of problems with this, which is why it's really interesting. And we need to find more of these kind of double supernovae to figure out why 2 stars that live for millions of years can explode at the same time. Doesn't make sense.
Yeah, there's one. Okay, go ahead.
So how much data is Atlas gathering each night?
I don't know about the raw data. That's a very good point. The number of I don't know if it's gigabytes or just in the terabytes of raw images. But it's yeah, I'm gonna guess mid 100 gigabytes or low terabytes. But it's not the petabytes. We're not radio astronomers. But it's terabytes of images together that are required to hold the tenure of the survey. But because you take flats and everything, and I don't think we keep all of the flats. You know what I mean? Like there's extra stuff, but it's a lot. It's a lot. There's big cables under the sea that help us bring that data back.
Oh yeah, we've got a question from the stream.
Yeah, it's saying, do you process the data on local computer systems or combined cloud systems, and how long does it take to train your model?
Sorry, can you repeat the start of the question?
Yeah, so basically it was asking whether you process it on local system or combined with cloud systems.
Oh, good question. So for my virtual research assistant, it's all on my laptop, and it takes only a few thousand images. My shtick in the AI and science world is very data thrifty algorithms. So I don't put whole images in it. I don't put whole light curves even. It's feature-based machine learning algorithms. So basically, I do a little bit of cookery on my data. I cook my data a little bit. There's some stuff that goes in raw, like the RAN deck, the position on the sky, and there's some stuff that I know is more relevant than other bits, because I've been looking at this stuff for years, and I can share my expertise with my computer. And by doing this and using real data sets, I can train things with only for Atlas, it was of order 14,000. The kind of stuff that I do for Rubin, because I'm using other extra fancy statistical methods called active learning, where I pick the data that are the most informative. I have trained for the Rubin Observatory a preliminary algorithm on only 400 examples. And it is working surprisingly well, and it's very stressful. I've not had time to do the analysis. All my colleagues are, oh, it works, I'll just use this. I'm like, calm down, please. Let me check that it works for real. It is very scary. It's scary when things work too well and you don't know why. It's just as scary as when they don't work and you don't know why. When they work well and you don't know why, everyone then starts using it, and then you have to tell them to calm down for a bit. When it doesn't work, they wait for you to get it to work. But yeah, you can do a lot of great stuff with only a few hundred examples if you're using the right data and the right features.
That's nice. Very efficient.
Cool. Do we have any more questions? Any more? Oh, yes.
Wondering about like the environmental sustainability of running the assistant.
So just worrying about the environment.
Yep, that's why it's cheap as heck. That's why I do things that are super cheap. It doesn't take any more energy than an Excel spreadsheet, because it's not like an LLM, like a ChatGPT. I'm not calling any of these things. It's literally maths I've trained myself. The thing I mentioned, like GBM, it's just a mathematical, like a statistical method. So it's just, I call Python, I call that little function, and it's yeah, it's just like running a small program on your laptop. It could run on my phone, easily on my phone. Like it could run on a laptop from 15 years ago, because it is that cheap. The thing that's maybe worth mentioning, I didn't realize until I started working in this field, what costs a lot of money often is not the processing, like doing the maths, because computers are really good at maths. Like they can do it so fast. It's holding data. So data storage is super, like, because it's loads of data. Just keeping the raw images just to make sure that we can do the science again. Keeping storage alive means electricity constantly and cooling down servers. So that's usually where a lot of the price comes from. And so for the super big things that are trained, like for these like Claude or ChatGPT, etc., they're using massive amounts of data, and that's partially where a lot of the cost comes from. The inference is also very expensive for them, because their models are like billions or trillions of knobs and dials they have to twist, and that's very expensive, that's true. But for astronomy, even if I reduce the amount of like calculations my model has to make, I'm still an astronomer that works for systems where we have to keep big pictures in computers somewhere so that we can do science, and that's where we have to be careful to like keep just what we need in and be thrifty.
Astronomy. I know of my understanding that it saves a lot of time with accurate imaging, a lot of labour intensive with the machine. You see, with that fact that you say it would take hours and hours and hours to see it individually, the naked eye. How has it improved and saved them time and money? Has it improved with the AI in astronomy? Because I know medical professions are using it for breast screening, that they're using it to save time and the person having to do the breast screening to assess if there's any lump in the breast, because there's not enough radiographies available, people to do it, or people to examine, not enough examiners. But how does it help astronomy in the real? I know, or basically just repeating the question, the answer, because it saves time. What it does, it saves money, and give more clear images, and then take it with the naked eye.
Can someone summarize the question?
Basically,
yeah.
just asking about what's the main benefit that AI has provided to astronomy.
Well, the machine learning stuff I was talking about, we literally can't do the kinds of surveys that we do without machine learning, because the amount of data we take every night is too much for people to keep up with. It would take like thousands of humans to do that data filtering by eye if we had to. So we just couldn't do sort of fast surveys like we're doing. We would be stuck at taking like one picture of the full night sky once a year and hoping for the best. So it's not just that it makes it easier, it's that it makes it possible.
I think we're good.
I think that was the last question there. So I just want to say thank you so much for taking the time out of your early morning to jump on and speak to us. I always love the way that you mix the technical with the fun and make it accessible to people. So yeah, thank you so much for coming to speak to us. So shall we?
Thank you very much and for listening. Have a good rest of your evening. Bye bye.
Now, is there any way that we can follow your work? Oh no, she's gone.
Oh, she just left
well,
us.
She does have social media pages which you can follow and have a look at her work. So yeah, thanks everyone for coming. Hopefully you enjoyed that, and then we have stuff out in the foyer. So please.